I'm going to try to tell you a few words about distance geometry. It's a topic on which I've been working since a while, since years now. This work is in collaboration with my PhD student, Simon Hengeveld, that is here in the audience. I gave a presentation yesterday in another session. And in this particular, in my presentation, I'm going to focus on the one-dimensional case. So distance geometry is it's a wider problem that where the target Euclidean space is in general can be in general of any dimensions. Here we focus on dimension 1. So I will start with an example directly in this dimension. Okay, and okay, on the side, maybe you'll notice there will be at the end some. I will mention to some applications to GPU with GPU programming and optic computing at the very end of my presentation. I will start now with a very simple example. So suppose we have a graph that represents an instance of the distance geometry problem in dimension 1. Points, I don't have a pointer here, right? No, I don't have a pointer. So vertices here represents points that needs to be embedded in the one-dimensional space. So in this case, it's this line that appears here in the bottom of my slide. And the numerical values that are associated to the edges represent the distances between the vertices that we want to be respected in the embedding. So here, imagine this is already an embedding of my graph by dimension 2. Now I'm interested in embedding in dimension 1 such that these distances between vertices are satisfied. Okay, so let's try. So we start with the example. I start to color these two vertices with two different colors. I try to put them in the one-dimensional space. I hope you can follow. So in this case, it's easy. I take 5. I take these two, and they need to be 5 units away from each other. Then I take another one. So I have now the magenta vertex. For the magenta vertex, it needs to be 2 units away from the green one, from the green vertex. And so I have two possibilities. So either I go on the right side or on the left side. And so I have two possibilities for this vertex. Then I continue. Now I have a brown vertex. And for the brown vertex, you see I have 4 total possible positions. And finally, I have a red one where I have 8 possibilities. Now it's a little messy there, right? And we don't understand what are the solutions actually. So I'll try now with the help of my screen. So now let's make order. So I will keep now on this at this level only the last vertex, so only the red one. Before doing this, okay, this I will tell you later. I forgot, I will tell you later directly. Now we keep here only the red ones. Here I have all the others. Now I do this step again. I keep only the last but first vertex, the blue, the brown one. Yeah, the brown. And the others are up. And then step again. And I have the first two on this line. So you see now, we are always in the one-dimensional space, but I separated the vertices in order to make some order there. And you see that there is a tree structure that appears. And so finally, the question that I was asking before, where are the solutions? The solutions are paths that start from this root and go under until they root a leaf node of this binary tree. So for example, this is a possible solution, this is a possible solution, and so on. But did I use all the information, the distance information, to construct my embedding so far? Actually not, because this distance is not exploited yet in my construction. And if I use it, so I put the graph here to have some more space. If I use it, I can, by applying the same technique, I can embed this vertex again. And so you see now I have 16 possibilities for this vertex. But actually, the only one that I can use is it's the position that corresponds to my original vertex, because this appears 2 times now, at the beginning, at the end. So the only feasible solutions are the ones for which this vertex is in this position here. Actually, we have two in this particular example. So what about all the other solutions that you saw around? They're actually infeasible, so I can cut them away. And this is the final set of solutions for my distance geometry problem in dimension 1. Okay, why I showed you this particular graph? This graph has a particularity. You have recognized this. It's a cycle. And cycles represents particularly difficult distances, so distance geometry in this dimension, because as you can see from the construction, every time I want to compute the candidate positions for the vertices, I use only the information about the previous layer, the previous vertex in the order that I can define on the cycle. But then the verification of the solution, so deciding whether a solution is feasible or not, this decision can be taken only at the last vertex. So this means that my search tree grows and grows exponentially with the sides, with the number of vertices that I'm using, and I can really select the solutions only when I reach the end, when I finish the turn around the cycle. So that's why we are particularly interested in this particular, when working in dimension 1, we are particularly interested in this kind of instances because these are the hard ones. And for the two applications that I was mentioning to you, the GPU programming and the optic computing, we need to make a fundamental step, which is to transform this, to represent in a way, this binary tree that I showed you as a matrix. Because then once I have a matrix representation, I can use GPU and optic computing to solve these hard instances. Okay, let's try quickly. Let's see how to do this. I will show you in a visual way. I didn't write many things, but it is important. Now, from now on, these points are not embedded the vertices, are not positions, are not just representations. So this is just a tree representation. So how to transform this into a matrix? So the procedure is the following. I take the all leaf nodes, and we know that these are potentially all different. Now, in my example, you've noticed that there are some positions that are the same. This happened because I used integers. And so there are the probability that the two vertices are positioned in the same place is higher with respect to the situation where I use real numbers, where this probability is as a Lebesgue measure equal to 0. So a very low probability, but of course not impossible. But potentially we can suppose that these are all different. Then we go to the other layer. Now, to go to a layer up, you see here for these two, I have only one. So I have to duplicate in order to fill a matrix, you know. So here I'm trying to construct the matrix row by row. So this is the last row with all different values. Here I have another row, but here we see that I have a copy. For every vertex, I have a copy. And when I go up, again, for here I have only one for 4 of this and for 2 of this. And so there will be 4 copies of the same vertex position, and so on. So I continue until I reach the green one, where they are all the same, because I have only one in the binary tree, and for the light blue, the same. So, okay, so now here it was a little messy because these were the positions of the original tree that I drew by hand. So, okay, I clean a little, but you see I have a matrix structure. If you can deal with the blinking, you can see a matrix structure. And now what I do with this matrix? First of all, before what I do, what are the, now I just draw these points, but what are the numbers? So the first, on the first row, I actually have all zeros, so I can remove it, because on this row, I have the positions of the first vertex that I can position wherever I want on the Euclidean space. And so I can consider, I put it in the origin. Then here I have a distance between the light blue and the green vertex. And it's always the same. Then other layer, I have the distance between the green and the magenta, or the negative distance, and so on. So if I continue, I have a positive distance, negative distance, positive distance, negative distance, and so on. So this is where I fill my matrix. And hope you got it, as I hope here. Yeah, in the example, we could take my previous example. We could take the last distance equal to something that doesn't match with all the rest. And in this case, distance is simply infeasible. Actually, what I'm going to do there, it's with the GPU and optic computing, it's mainly to verify if the distance has solutions, first of all, and if there are solutions, where are they located on the matrix? Okay, so so more or less you follow the way I construct this matrix from the binary tree. Of course, you saw that I duplicated data. So when I work on the matrix, instead of working on the binary tree, I also duplicate the number, I increase the number of operations that I need to do. But it makes sense then when to use this approach by matrix, when I use devices that are more powerful than the normal transistor-based computer, or a normal CPU. Of course, the GPU is transistor-based, but okay, it's a special kind, let's say. Now, see if this is, so if this rectangular shape that you saw in my slide, hopefully, is my matrix, you can take a column on this of this matrix and make the sum of the elements. Once you have the sum, this represents the position in the Euclidean space in dimension 1 of the first vertex. So it's the vertex was called with light blue in my slides. And at this point, since I suppose that this vertex is in position 0 always in the origin of the Euclidean space, I can verify the feasibility. So I come back to your question. I can verify the feasibility of my solutions by verifying whether the last vertex, or if the sum of these elements of the column correspond to 0 or not. If it's 0, if 0 appears again, then the distance is feasible. If it doesn't appear, it means that the distance is not feasible, because at least one of the distances is not satisfied. And now, when we work with GPU, we can assign. Okay, let's say I will present the ideal approach. Let's say I have a GPU with as many threads as I like, and so I can assign each column of the matrix to a different thread. And at this point, every thread is in charge to make one sum that will be performed in parallel with all the other threads. And so in one shot, let's say I have a matrix, so the complexity of making all the sums will be n squared. In this ideal GPU, I could make in n steps the verification of all the possible solutions inside related to my instance in dimension 1. And of course, when I do this, I get only the answer. I get two pieces of information. I get information whether the distance is feasible or not, and I get, okay, it's a byproduct, the position of the first vertex, which I know it should be 0, but I don't know all the other positions. So in case we use for this GPU approach, we should first of all, it's back. Thank you. Okay, so I continued. So this is a paper that it appeared on the proceedings, and there is only one thing. Okay, it's too small, but here in the paper, also in the other one that I will show in a second, we talk about matrix by vector multiplication. So with what we can in both GPU approaches and optic approach that I will show in a second, we in general we talk about performing a matrix by vector multiplication. If you want, in my example, it's like having a matrix where I only have the distances without the difference in signs, and the vector contains only ones and minus ones. It's exactly the same thing. But okay, here you will see written somewhere matrix by vector. But I mean exactly what I showed you in the example. The example is a little simplified for presentation purposes. And here we have some computational experiments. And so I little lost my line of what I was saying before the slides reappeared. But OK, if something not clear, don't hesitate to ask. And here, so we compare the new approach with an algorithm that performs the search. We call it the branch and prune algorithm, BP algorithm, here in the table. And this algorithm performs a search on the binary tree. Instead, the second two pairs of columns in the table represent the approach that I just showed you. First of all, in the sequential. And as I mentioned, since we include more data, we include more, we add operations to be performed, the sequential version of this algorithm based on the matrix is much more expensive than a search on a tree. But when we move then to GPU, we see that it was worth to make the modification, because in GPU, of course, here we are not in the ideal case of one column per thread. We have something like 512. Oh, no, wait. Yeah, OK, I have 512 by 512 threads. And the size of the matrix is much bigger. Yeah, it's 32 vertices, so 2 to the power of 32 possible solutions that are verified. And OK, you can see the numbers. We have 30 seconds for the last experiment, the largest, 30 seconds on one side and 2 seconds on the GPU to make the same verification. Yeah. OK, this is yeah. Yeah, it's a good question. It's a good question. I didn't want to mention because it could take long, but since you asked, I have to say now. So there is a trick. OK, there is a little problem here, because when we verify all these sums, in my example, I was working with integers. So I finished the time? Yeah, OK. OK, very fast. I work with integers, so I can verify with there are no round-off approximations where I perform the sums of the distances and so on. With the real numbers, I will never find 0, 0.0000. I find something like with a tolerance of 10 minus 3, minus 4. But when you start to combine these few numbers, 2 to the power 32 times, there are several combinations that go very close to 0, but they are not 0. So the problem is to verify, to set up the epsilon, the tolerance. And so this is quite tricky. So in this, so when it's too low, we get 0. It says there is nothing anywhere. When it's higher, I don't remember exactly here, but I think it was quite high, 10 minus 4 maybe, tolerance for the epsilon. And we get this number of solutions. As the size of the instance grows, we have more probabilities to have combinations that go close to 0, but they are not 0. And so I count more. And this is quite important. I say this in 30 seconds, if I'm able to do. Important in this optical processor. Now, this is another paper published last year on Journal of Optics that inspired this paper on GPU. Where in practice we try to make the same operations, matrix by vector multiplication, by using an analog computer that works with the light beams. It's not a quantum computer. It just exploits the light. And even though we use interference here, which is one of the ingredients of quantum computing. And here, the idea is that the detector at the very end tells us if we don't have light, it means that we are close to 0. But how close to 0? This is much more complicated to verify here, because at least on a digital computer we can count the digits. Here we check the intensity of the light with the detector, so the precision is much lower. So actually, with this paper, we showed that the actual implementation in hardware of this optic processor for matrix by vector multiplication can have this quite important drawback. And so, okay, research is going on to try to solve this problem. Okay, it was my last slide. Thank you very much. Yeah, good question. Okay, the metric side. So in this orientation that I have, so I have on the rows, I have the number of leaf. So the number of columns is the number of leaf nodes of the tree, which is 2 to the power of n. So yeah, so number of columns is 2 to the power of n, where n is number of vertices in the instance, and on the number of rows is n. So it's n by 2 to the power of n. So the number of columns grows exponentially, and the number of rows grows linearly.